Hello friends, it is Ben again. This is yet another of the videos to help you get through the assignment that we're doing for the Math Tech class. Today's actually, I'm hoping is going to be relatively easy, okay? Uh, but with regard to this, I want to give y'all the heads up that I have purposely got slightly different data for you to work with than what I have. Some of it's the same and some is different. So you may get exactly the same answer on, I think, the first and last ones, but you may get different numbers on the middle two. Okay, so there's four things we're looking at, and we're going to launch right into them. Okay. But to explain the theme for today is taking a look and comparing different sets of data. If you're wondering why would you need to do this sort of thing, this is really the kind of thing that you do in the sciences. Say, for instance, that you are testing a new vaccine, okay? If you want to show that your vaccine works better than a placebo does, placebo, by the way, is something that they give people that doesn't have any active ingredients so that they can compare, having a medicine and not having a medicine and still eliminate the belief that, they did or didn't receive something. Okay. But in any case, though, that sort of testing, you need to be able to do something to statistically say, yes, I've got solid enough evidence to actually say that I have solid evidence. Okay. So the thing that we're going to look at is hypothesis testing stuff. And what that means is we're going to again calculate we're going to calculate a p-value for some data in order to help us determine, is the likelihood that this data could happen completely at random, is that likelihood small? So basically we're testing to see whether the data is a fluke. And if there's a large p-value, that says there's a large probability that, yeah, this could just be a fluke. And if there's a small p-value, it says, no, there has to be something going on here that's causing it. It doesn't necessarily say, that the cause is what we think it is, but it says that there's got to be some kind of cause. All right. So with regard to this, I'm going to launch right into it. Hopefully, at least. I'm sharing. Nope, I don't want to do that. I want to share that desktop. Okay. So the thing that you are seeing on there is data for 2 different years of retail electricity costs. And so the notion is that if you put household 1, 2, 3, and so forth down this side, that household 1 had a cost for electricity per kilowatt hour of $20 in 2009 and $19 in 2010. Okay. So this sort of thing is what you'll do when you have a paired difference, where you want to see whether two things are different and it's paired up. So the same household in 2 different years is an example. But you could also look at it like if you had somebody that you put on a diet, you could measure the efficacy of the diet by saying, did they lose weight? And so you look at their weight before and after, and you subtract and get the difference. Or you could do something with maybe a vaccine or some sort of medicine that was going to have some measurable difference, and you have a before and after sort of thing. Okay. So with what we're doing here, we're going to make use of a formula thing, and we're going to say to this equals the 2009 number minus the 2010 number, okay? And then for that, we can just copy it down to the others, right? And just looking at that, I can see it feels like that is probably giving us more negatives than positives. So I feel as though the price did go down, but there are some where it went up. So maybe that's balancing out. Mm. So what we're going to do in order to test this is what's referred to as a paired difference with a t-test. And if I remember right, fingers crossed here, if I remember right, this has something built into it that we also need to check about. Remember the other day that we looked at the normality plot to see whether or not something was approximately normal, and it basically looked to see whether it lined up on a straight line or not. That's what we're going to do, only it turns out it's built in, and I did not know that. All right, so what we're going to do here, we've seen this kind of thing before, and again, I don't remember whether the window will show for you or not. So I am going to jump in and out of some windows for a second and try to make sure that you see it. So help me remember here. That was a dumb thing for me to ask, but I'm going to try to remember that F6 is the location that I want to put the results at. All right. So I'm going to go up into the tools menu, and on the pull down, one of the options is data analysis. All right. Now I am going to stop share, share again in order to, show you that window. So on the data analysis, you have a bunch of different options there. And we're going to later today talk about ANOVA testing. But for right now, we're looking for t-testing and see paired. So t-test paired two sample for means. Okay. And z-test two sample for means. And so we're looking for the paired two sample. And we're going to go ahead and tell it that that's okay. And we're going to now have to tell it to do the range. And I'm highlighting first the 2009 numbers, nothing more, nothing less. And then, actually, I don't know for sure if this is showing for you. So let me go ahead and do that same thing, stopping sharing and sharing again in order to make sure that you're able to see that. Okay. So the thing that I did was to click on one of the little interactivity buttons to tell it that I was going to then choose a particular area there. I'm going to leave the thing where it says hypothesized mean difference to be blank, and it will assume that we're thinking about that as 0. Here where the alpha is 0.05, if you're doing one of these p test sort of things, p values, 0.05 is the standard. Doesn't actually seem to figure into the calculation anywhere. But what you're looking for is if the final result is less than 0.05, then that's telling you have strong enough evidence. If you are doing a medical application, often you'll need to do something like 0.01 because it's harder to get small numbers. All right, I'm going to tell it my output range here was F6, as I recall. I'll tell it that's okay, and it's probably going to dump us out. So I will go back and share screen over again. Okay. So the stuff that it dumped out here was the t-test paired two sample for means. Now that did not get us a normality plot. Let me go back and try that again, just to see whether I missed something. Data analysis. Okay. Nope, it did not have that built in. Okay, so this was assuming that our normality plot would come out okay. So maybe we better go back and see what we can do about that. Okay, so we'll We'll look at that here in a minute. But looking at what we've got, and I don't need that much space in there, it drags out all these different numbers for it. And what you're going to have to look at is either this piece here, okay, or this piece here, okay. So the thing that we're thinking about with this is the probability, the p-value, that we would have numbers that showed up like this if the variation was just random. So taking a quick look here, the one-tailed test. So this is looking at the probability that, since it says less than or equal to, that the 2009 numbers were less. And it says that we're getting 0.4 for that. And the probability for a two-tailed test is going to just multiply that by 2. And so we're ending up with 0.8. So this says that we have an 80% chance of having numbers that are different from each other, kind of either way, just at random. So this is not strong evidence, okay? And we do have that concern about, do we have something that is approximately normal? Let me see whether I can get that through a different routing. And actually, I am going to stop share and pause the video because you don't need to watch me just experiment. So, oops, and that was the wrong button. All right, so I'm going to pause for a sec. I'll be right back. Okay, I'm back. Turns out that a tool that I was able to get to work in a different setting isn't going to work on this. So we're going to go back and do something that we did on the previous day. So bear with me as I show you how to do this all over again. So I'm going to share the screen here. Okay. And then I am going to come over here. Come on, there. So remember when I subtracted those things and then did not use them? So we're going to use those now. I'm going to copy them and I'm going to put them down here. But when I paste them, I'm going to paste special, and this will hide things from you, unfortunately. Hang on. I know how to fix this. Share screen. I'm just going to share everything on there. Okay. So you should be able to see it this time. I am going to paste on that. And what is it I'm going to paste? Values. All right. Not the formulas, not the formats or something. And I do not need to transpose it. I'm just putting those values down there. Okay. Notice it stripped all the formatting off and everything. But I'm going to go ahead and sort those. And I hope it's got that right. Okay. And then if you remember what we did, we went ahead and numbered things. Okay. I guess I should have just copied those ones there. And then this is the tough one to remember how to do. We're going to say equals norm inverse, norm.inv, parentheses, and then we're going to have that thing over there. So that was A18, except I'm going to need to put parentheses around it. Parentheses, A18 minus 0.5, okay? And that was basically to keep an error from coming up, divided by, there's 9 of them, so I'm going to say divided by 9, comma, okay? And now we're going to just say 0 for the mean and 1 for the standard deviation. You could put anything in there. That part doesn't actually matter, okay? I hit enter and it will do a calculation. And then I copy those down so that it has a bunch of those. And now I'm going to zoom out and take those numbers together, and I'm going to do one of those scatter plots again. So to do that, we had to go to the insert menu, and nope, sorry, wrong insert menu. The insert ribbon menu in order to find the scatter plots. And remember, we do not want the scatter plot with lines, just with the dots. And we get something that looks like this. And I'm going to change the title to it to say normal plot. Okay. And I'm going to now add a trend line to it just to kind of eyeball it there. And we don't need to have to be very fancy with that, but we take a look at it and we see, yeah, the data did more or less line up. Okay. Not perfectly, but it more or less lined up. So that means that we have something that's roughly normal probability on the differences. And then with this paired difference stuff, we, if we were trying to show definitely that the 2009 numbers were smaller, then we would look at the one tail probability here. But we really want to just figure out whether they're different. So we look at the two tail probability here. So that 0.8 is way larger than our 0.05. So that means this is not strong evidence of a difference. Okay, so that's the kind of thing that we'll have to do on these. And each one of them is going to be a little bit different. But what I would like for y'all to do on this is to do the normal probability plot. You should really have done that first. I thought I was going to be able to get it to just happen for us, but I should have done that first. But do the normal probability plot, get an idea there. And then go ahead and once you've confirmed that your differences are roughly normally distributed, then you go ahead and use this t-test. And it just allows you to pick out the appropriate stuff and boom, boom, boom. Once it gives you this on your progress report, once it gives you this p-value of 0.804, you would be reporting back, we don't have strong evidence because my p-value is too large. You want small p-values to mean you have a small probability of being wrong. Okay. All right. Now we're jumping ahead to one of the nice things about statistics is that it's always super duper cheerful. Everything is always numbers about death and cancer and stuff like that. Here is one of those. I stole the idea for this problem out of a stat book, but then I generated my own data for it. Okay. And bear in mind, the data that I gave y'all will be slightly different than mine, so it may not turn out to be the same. Okay. But the process is exactly the same. So here we have these two cigarette brands, Laramie and Morley. Those are two fictional brands that appear in TV shows and stuff. And we have taken a sample from 25, I think it is, cigarettes from Laramie and 36 for Morley. Okay. And because we think that both cigarette brands are taking their tobacco from the same tobacco fields or something, or otherwise we believe that the variation between them should be the same. Okay, so sigma is standard deviation. It's something that talks about how much things vary. If we have some reason to believe that that standard deviation is the same, then we will use a certain technique with this, and we'll use a different technique if we have no reason to believe they're the same. All right. Now, one thing to notice here is that we have more data points for one than the other. That gives you a clear signal that these cannot be paired differences. These are independent samples. So before continuing on with it, we really ought to check our probability or normal probabilities. So I'm going to take that there. And actually, I'm going to include the label for it. So there. I'm going to copy it over here. And then I'm going to put those numbers there, 1, 2, 3, you know. So, yep, it did turn out there were 25 of them. And then I'm going to do my normal probability thing. So equals norm.inv. And then we're going to do that E5 there, but that was not quite right. It had to be parentheses, E5 minus 0.5 divided by, since there's 25 of them, we're dividing by the 25, okay? And we'll just put 0 and 1 in there. Doesn't matter really what those are, but but you do need to have the standard deviation part being negative or being positive. All right, so then I copied those down across there, and I'm going to real quick just highlight the two things. I'm going to go to my insert menu, get it to do a scatter plot, and man, oh man, those do not look. Oh, you know why? I messed up. You know what I did not do when I got started on this? I forgot to sort these. So you're, as usual, you're learning from my mistakes. So I'm going to go in here and do my data sort and continue with the current selection. All right, I should have done that first. Now when I highlight them and tell it to insert the scatter plot, it looks pretty much like a line, but it's a really close to vertical line. I'm going to mess with this a little bit by coming in here, and I thought I could mess with the horizontal axis. Yep, there we go. And since all my numbers seem to be between 20 and 30, I'm going to change the bounds to be between 20 and 30. And now we've got that in there. And if I add a trend line to it, it looks, it's not very normal, but I'm going to change my chart title here to say Laramie normal plot. And then I'm going to go through and do the exact same sorts of things with the Morley part, okay? So maybe I will go ahead and pull this down here since we're going to have plenty of space and stuff. Maybe I will put the Morley part on the other side or something. All right, so I'm copying all of those, and I am putting them maybe right here. And I'm going to go ahead and copy those numbers that I used last time down here. And then I'm going to go ahead and continue it on down to 36. All right, now remember that formula that I had a minute ago. I'm going to copy it and paste it on down here. I would like to paste it down here, but of course, this being, oh, I need to paste it down here, and then I have to edit it. Do you remember when we divided by 25? This time we have 36 numbers. So I need to have a 36 instead, right? And then I need to copy it if it will let me copy below the bottom of the screen. Yep, it will this time, but it wouldn't before. No idea why. All right, so we're going to go ahead and highlight those two columns. And then we're going to go to the insert menu, get ourselves a scatter plot. And I'm going to put it a little bit higher here. Oh, wow. Oh, Laramie disappeared temporarily. All right, so this is going to be the Morley normal plot. And just like before, I forgot to sort. So I wonder if I go ahead and sort them right now. I have to miniaturize it, which means it's completely unreadable to y'all, but I have it miniaturized so that it all is on the screen at the same time. And then I can go to data and tell it to sort. Don't expand the selection. And there, okay. So now if I zoom in, y'all can see it looks pretty much like a line. I'm going to change it to be going from 20 to 30 and enter, close that. All right, so now y'all can see that if we put a trend line on there, it looks like it pretty much lined up, okay? We don't really need to know the equation of the trend line. We don't really need to know an R-squared value. We're just basically looking to see, did that more or less line up? All right, so pulling out here a little bit, jeez. All right, so now we're going to go back and we're going to do the actual data analysis because we have things that we feel like are more or less normally distributed. And so I'm going to, for that, tell it tools, go down to data analysis, and we look here at our t-test stuff. The t-test paired to sample for means won't work for us because these are not paired. They were independent samples. So we're going to look down here to the t-test to sample assuming equal variances. This time we're assuming that the variances were equal, okay? And we tell it that's okay, and it gives us the input stuff, and we're going to take and click on one of them and highlight the Laramie brand, tell it that's okay. And then I've had some problems with this, so when I click on the other one, I'm going to miniaturize the view, or not, because it will not let me do that. Okay, but it will let me drag down. Okay. So now I've got those two things chosen there. And I'm going to say for my output range, and I've got to kind of just look here to make a guess. I think if I make my output range like B48, then it won't be covering anything up, okay? Now, if you all miss that and choose new worksheet ply, then you'll have a completely new sheet to have things on, and you need to label it so that I can figure out which thing's which. It would be much easier if you just put your results on the same sheet, okay? So with the information that we end up with here, we're gonna look along here and see that if we are trying to show that the first one, the Laramies, have a lower amount of nicotine than the Morleys, so the less than or equal to, then we've got about a 0.045, so a little bit less than 5%, okay? If, on the other hand, it was just asking, do we have evidence that they're different, then the evidence isn't as strong, because evidence of difference, these two-tailed tests, are a slightly more robust sort of thing. You end up not getting strong evidence as often because it's just harder to get the evidence. So in your progress report, you may have different numbers. And I need you to go ahead and report. Why don't I ask y'all to go ahead and report on, in particular, the two-tailed test here, okay? So in your progress report, say something about, like if you end up with a 0.09, yours may not be exactly what mine are, okay? But if you ended up with a 0.09, you would go ahead and report and say my p-value was 0.09, which is more than 0.05, so I don't have strong evidence. If, on the other hand, you got like 0.03 or something for that two-tailed, because I'm going to ask you to do the two-tailed, right? If you got something that's less than 0.05, you would say you have strong evidence, okay? Because this p-value kind of, sort of, is your probability of being wrong with what you think the evidence says, okay? All right, and leave all that stuff on there. If you can kind of tidy it up where that, it's easy to read, it would sure be nice, okay? All right, so the next one that we're looking at is looking at independent samples with probably different sigmas, okay? How do you know when it's different or the same? It has to tell you. That's all I can say right now. If you were doing this, say for a lab from a bio class or something, then something from the context would tell you whether or not to assume that the sigmas were the same or different. My suspicion is most of the time you're going to assume they're different, okay? But the question that we're dealing with here is the stopping distance for drum brakes or disc brakes. So I don't know if any of y'all are car people, but disc brakes and drum brakes are two different kinds of brakes that you have in your cars. Most cars will have disc brakes on the front, and some cars will also have disc brakes on the back, but some will have drum brakes on the back. They are cheaper to manufacture. That is really the main difference for manufacturers. For your purposes, you never have to worry about disc brakes getting wet. Because of the way they're set up, any moisture that gets on them just instantly gets knocked off by the pads themselves. Drum brakes, on the other hand, can get wet. And with both of them, if the brake pad itself gets brake fluid on it, you'll know it. Anyway, so the question here is there a difference in the stopping distance from, I think it was 25 miles per hour? I'm trying to be metric. So 25 miles an hour. Let me change that and say 50 kilometers per hour, because the distances I had recorded here were in meters. Weirdly enough, I was getting meter distance. I looked up some examples for this, and I was getting meter differences for miles per hour, and that was weird. But anyway, from the same condition, is our stopping distance in meters going to be different? So, like before, we're going to go ahead and do the check about our normality. And so I'm going to drop this over there. And then I'm going to put numbers beside it. Okay, so there's 21 on that. So then y'all should check yourselves, see if you know how to do this. Equals norm dot inverse parentheses, another parenthesis, this number over there, don't type it in to just, get the F4 wherever it is you put it at, minus 0.5, and that's to prevent a weird error, divided by, we saw that there were 21 of them, okay, comma, 0 and 1, okay. Then once you've got that, actually I should maybe label this, but once you've got that, you drag it down to the rest of the things beside it. And then you can do the insert scatter plot like so. What did I forget to do? The same thing every time. I keep forgetting it, but we know how to fix it pretty easily. So come on. Drum norm plot. And so I'm going to move that out of the way. Close that. And I'm just going to highlight the things that I should have sorted in the first place. And I will have to say data and then sort. No, do not continue or do not expand. Use the current selection. All right. So that looks like it's fairly normal looking, right? All right. And I think I'm going to take this stuff that we've got right here, and I'm going to drag it back over here a little bit closer, just to kind of get it where it's not taking up a whole lot of space. All right. Then I'm going to go ahead and do the same thing with the disc brake. And I put it in kind of the wrong spot. And I'm going to put numbers alongside there. And it looks like we have 19 of those instead of having 21. I'm going to copy the same formula. Oh, ha ha ha. Except, you know what I'm going to do? I'm going to sort it this time. And continue with the current selection. All right. So I'm going to copy that formula and paste it here. And then I'm zooming in so that I can show y'all I'm changing the formula. It needs to divide not by 21, but by 19, because that was the sample size. And then I'm going to take and copy it down to those. Okay, they should all be increasing and stuff. And then I'm going to, like before, highlight the two numbers, columns of numbers, and I'm going to insert a scatter plot like so. And I think I will grab that scatter plot and just move it over underneath the other one. And the title for it was disk norm plot. And I don't have to hit enter at the end of every one of those. And I'm going to add a trend line. You don't really need to add a trend line on this. You can see they line up, but might make it a little bit easier to see. All right. So now we've looked at both of our bits of data. They more or less look like they're appearing on a straight line. If anything, I think maybe two of the drum ones look like they're off, right? And so you could hypothetically figure out those were the two with the shortest stopping distance. You could remove those from your sample because you believe they're outliers, but I don't think they're going to mess it up that much. I got to tell you, I'm not a good statistician. I always look at these and say, good enough. A good statistician, a good scientist would not do that sort of thing. They would worry it over a little bit more. All right. But now that we've got things to that point, we're going to go ahead and run this t-test part. This thing that I keep doing of checking the normality of them really is only something you have to do for small sample sizes. Once you get a sample size of more than 30, it's almost always approximately normal. So we kind of shrug at that point. But, all right, so we're going to run this t-test, and I'm going to put the result there at B30 once we get it. But testing you, what do? That's right, tools. Yeah, I would much rather have y'all with me here so we could talk through it. Tools, data analysis, to sample, assuming unequal variances. We tell it that's okay. Now we have to tell it where the two columns are. So I chose the first one, and then I chose the second one. Come on. Yeah. You got to make sure don't get any blank spaces in there. That'll really goof it up. And we don't have anything about a hypothesized mean difference. The alpha 0.05 I mean, it's there, but it's, yeah, not going to show up. The output range, what did I say? B30. We tell it that's okay. And now we can take a look at what we ended up with. It looks like, oh, and we ought to be saying, is there a difference? That's what we're talking about. And for a difference, then we would need to be thinking about the two-tailed test. So for the two-tailed test here of getting a difference, we've got 0.622. That's way more than our 0.05. So that means we've got really weak evidence. So it doesn't really look like our particular set of data, which I made up, our particular set of data doesn't really show us that there's a significant difference between the drum brakes and the disc brakes with their stopping distance. Okay. All right. Then for your progress report, you should put that note in there. I looked at this and here's what my p-value was, and tell me what you got. And then if it's less than 0.05, you say, it's strong evidence. But if it's more, you say, it's weak evidence. Okay. Small probability means a small p-value means a small chance that you're wrong. Okay. And that means strong evidence. All right. Let's do one more here. Right. This is a totally different trick. It's referred to as ANOVA. Okay. That is an abbreviation for analysis of variance. And we're going to do the one-way ANOVA testing. And what it does is to take a look at a bunch of samples, not paired samples, but at least 3 different samples. They can be totally different sizes and stuff, but every example I ever find is always exactly the same size. So I don't know what's going on with that, but the theory says, that they can be different sizes. So what this test actually does is to look at how much variation you've got in your samples and see what whether the variation between 2 samples is more than there is within a sample. Does that make some sense? Hopefully. So if at least one of the samples is way different than the others, then you'll get a small p-value. But doing this is actually, if anything, quicker and easier. Let's go ahead and see what we do with that. So every time so far, I've had us do the normal probability plot, right? And this is built into the ANOVA. I don't know whether it will plot it someplace where we can see it easily. But we're going to say tools and data analysis. You go up to the top, there's 3 different things: ANOVA, single factor, 2-factor with replication, and 2-factor without replication. So the 2-factor and with and without replication would be about looking at a chart where you have 2 different variables on it. The particular variables we've got are just different shifts producing the some widgets that they're selling. Okay. If you wanted to do 2-factor, then you would be looking about, well, does the day of the week, which is the stuff listed along the side, is the day of the week important as well as the particular shift that you're on? We're just going to do the single factor. We tell it okay. And now it wants us to do our input range. If you can read that there, you'll notice that it has a range that has to be contiguous. They have to all be next to each other. So I'll hit the red button and I'm just going to highlight the 3 columns that I've got there. Tell it that's okay. It does have the option of whether to have it grouped in columns or rows. And then for our output range, I am going to tell it to do C16 because that looks like it's a good spot that's not going to overlap with anything. Actually, you know what? That's probably not a good idea. Let's do like G4. Okay. All right, so that made it all appear on the screen at once, whereas if I'd done the C16, it would have all been on the screen. So your I never know whether to say ANOVA or ANOVA, but it collects together all kinds of statistics like the count of them, the sum, and the average and stuff. So just from looking at the averages, you can tell that these are getting different averages. 158, 192-ish, and 112-ish, you know? But the thing we're really looking for is our p-value down here. And it is the question of what is the chance that these all three came from the same population with the same averages? In other words, these three shifts at a manufacturing plant, what's the chance that they all have the same sort of production amount? And if you look at that, it says 5.96E minus 0.05. And right, and I'm going to take and copy that to here. And then I'm going to type that that is equal to point. So if it says -5, then that means there's going to be 1, 2, 3, 4 zeros before it. 5, 9, 6, 1. Okay. So just emphasizing there. You don't have to really type that part, but I wanted to put it in there to emphasize to y'all. That's a very small number. It's way less than 0.05. Okay. So this is saying we have very strong evidence that the averages of these things are significantly different. Okay. So you would reflect that sort of thing in your progress report. You'd say, here's what my p-value is, blah, whatever you end up getting. And if it's less than 0.05, it will be. Then you've got strong evidence that there's a different average production there. If you look at this, it ends up saying that the third shift has a lower production rate than either of the other two shifts. I spent a little while in manufacturing. Yeah, that tends to happen because you tend to have a lot more maintenance stuff that you have to do on the third shift between 11 p.m. and 7 a.m. So anyway, that's what we got there. I'm going to let you all go and see you in a few minutes, actually. So.